explains part of it. Oh, can you get that? Thanks. Thank you. Okay, everybody here? Mostly here? So I was just having a conversation with a couple of the students, a couple of you up at the dining hall, and I know it's a lot of work at night, and a lot of analysis, and a lot of questioning, and a lot of seeking out why things aren't matching. That is exactly how you should be spending your time. When you get an answer that is unexpected, and you go step by step, by step, by step, and you try to compare it with another one, or you try to go through each term and figure out which term maybe you're messing up on, that is validating, that is closure, that is using other measures to try and confirm your data, and that is exactly what all of us at the back of the room are looking for from you. And so it can be frustrating, it can take a long time, but that's why you're here. If everything was set up so that it worked perfectly and met all of your expectations, you don't need to be here, right? We're trying to provide you with the opportunity to have those challenges. And so that when you leave here, you know exactly what to do when you get home to your own lab. Like, oh, well, I get a nice spectrum. Do I believe it? No, I should go measure it with another instrument, or I should check all these things. That is what has to be just part of your everyday protocol of how you deal with your data. So some of the things you did last night probably took longer than necessary, like trying to figure out where the data are, what the file names are. That can be incredibly frustrating. That you can fix as you move forward. So we're doing a lab this afternoon that's going to be very similar. We're going to be working on a spectrophotometer. We're going to be working with the AC meters. So think about the things that were frustrating for you last night and make sure those don't happen today. I had a very rigid file naming convention in the spectrophotometer, which helps you out. It has the information you need to actually process the data. Do the same thing with the AC. Come up with a convention where you know which AC meter it was. It should have the serial number in the file name. It should have the temperature in the file name. It should have the sample code in the file name. Make sure that every file name has the same number of characters so that you can read it in automatically in a program and parse out that information, like temperature, to do an automatic correction. So come up with a convention. Come up with a Google document that is a list of all the file names, who collected it, what has happened to it, because you have this data forever. You walk away with all the data that you collect here. You might as well have a provenance for it so that you can go back and use it to test some model that you might develop next year. So make your life easier by putting in a little bit more time. Every time something seems like it's wasting your time, figure out how to improve your efficiency and make it work in your favor. Okay? And also know that we're up late at night too. So I know that doesn't make you feel any better for being up late, but it's only 4 weeks. Yes. Yes.
If you're here sleeping mode, these lectures you're going to miss tremendously. So
yeah.
I'd rather you do a little less fresh in the morning.
Yeah. And so you can prioritize. I mean, we give you, the other thing we do is you take all of this with you, which means that if you didn't get to something, you can do it when you get home. And you can email it to us, and we will give you the same comments that we would have given you from the back of the room. By taking this class, we're sort of your resource for the rest of our lives. So, all 190 students. Okay, so I'm going to give a little introductory lecture on scattering, and then Kurt is going to give a lecture on how you model scattering functions. So I get the easy part, Kurt gets the hard part. So I just want to remind you that we talked a little bit about scattering theory and about, again, what are our assumptions when we're making measurements of scattering and thinking about, understanding what the intensity of this light is, what the intensity of this light is, being able to calculate the intensity of the scattered light, that you have a known path length, that if there's absorption, you can figure out what the absorption is so you don't attribute it to scattering. So all of those things you'll have to think about when you're looking at absorption meters. We talked about geometry of scattering and how you determine the solid angle of scattering in 3 dimensions. I could go over it again if you want after the class, if you feel like you want a refresher on that 3-dimensional geometry, in order to derive that the solid angle is sine theta, d theta, d phi. And I'm happy to do that. Remember the volume scattering function. If we have an incident light incident on our target volume of interest, there can be scattering at any angle theta from the direction of propagation of light into the backscattering, so from 0 to 180 degrees, or 0 to pi radians. There's also a 3-dimensionality to that, so in addition to being at some angle theta, it can be at some angle phi, right, the azimuth angle. And so when we look at graphs like this of the volume scattering function, it's not providing us with any information about the azimuth. So either it assumes that it's homogeneous with azimuth angle, that it's uniform around the azimuth angle, that the scattering at this theta is the same as the scattering at the theta, the same theta but in this direction. That's what this graph will tell you. If that's not true, then that means that you have one of these for every phi, every azimuth angle. So this represents the magnitude of the scattered light as a function of angle. This is the back scattering. This is the 90-degree side scattering and the forward scattering. If we add up the scattering, if we integrate and add up everything under this curve, we get the whole total scattering coefficient, right? So it's essentially having light come in from the bottom and being scattered in all these different directions. And imagine having a little sensor that could measure that and measure that and measure that, measure every single scattered photon. That's the scattering coefficient, right? So that's integration under this curve. And then you multiply by 2 pi because that's your azimuth angle from 0 to 2 pi all the way around, okay? That's what this part of the integration is. Okay. So we talked about forward scattering and back scattering. The forward scattering is in this hemisphere. The back scattering is in this hemisphere. Remote sensing, very interested in the back scattering. It's much lower in magnitude, but it is why we see the ocean. Right? I think Kurt may talk about phase function, so just a reminder that it is just the volume scattering function that's been divided by the area under the curve. So it's a way of looking at different shapes of these curves. And I'll show you a couple of different shapes, and Kurt will show you how you model the shape of that curve. And so the scattering function is just the shape of that, yes.
So is this volume scattering function, well, as a function of theta, is this for just water without,
Yeah.
Is it anything?
It is.
Only?
It is, I believe this is out of a paper that Emmanuel and I wrote about modeling volume scattering functions for some harmful algal bloom, probably Procentrum micans.
But follow up, all kinds, pure water and big particles and little particles and air bubbles and all that, all have different volume scattering functions and phase functions.
Mm-hmm.
We'll see some of that in the next lecture.
Mm-hmm. They're very variable. And so you can have a volume scattering function for a single particle, and you can have a bulk volume scattering function for the sample of accumulated particles. Because it's just the measurement of the angle, right?
Is the back scattering always, there are different ways, back scattering always less than the forward scattering?
No. Sometimes it's equal. Yeah. But in the ocean, if you measure the volume scattering in the ocean, yes, it more often looks like this. Right? Okay. Oh, and yes, and this is spectral. This is at every wavelength. So every wavelength might have a different magnitude of scattering. Okay, so the parameters that we're interested in that influence scattering are, first order, the concentration of the particles. You have more particles, you'll have more scattering. That is always the zero order source of variability. It turns out that size of particles makes a huge difference in the scattering properties. And it's not the absolute size, it's the size relative to the wavelength of electromagnetic radiation that you're considering. So we talk about particles on the order of microns, and we deal with light on the order of hundreds of nanometers, or tenths of microns. The same theory works for infrared, which is a longer wavelength with bigger particles, or microwave with even bigger particles. Okay, so the theory doesn't change. It's the relative amount of relationship between the diameter of the particle and the wavelength. The refractive index relative to the surrounding medium. The refractive index describes how the speed with which light propagates through a medium. And so as you move from one medium to another, the wave will speed up or slow down, and that's described by the refractive index. It also matters if the particle absorbs light or not. Okay? And particle shape plays a really important role, and I think that's one of the areas that we know maybe the least about. I think people looking at the effects of shape and orientation of particles. We always say, oh, well, they're randomly oriented, so it's sort of like they're spheres. But I think we probably need to be moving away from that, because phytoplankton certainly orient themselves in a flow. Okay. So go back to the electromagnetic radiation. Remember, we have oscillating magnetic and electric fields. They oscillate perpendicular to the direction of propagation. What I didn't mention last time is they may be polarized. We have a whole lecture on polarization coming in week 3, Ken? Next week? Oh yeah, next week before hydrolate. Okay, and so the fact that radiation may be polarized adds a whole other level of complexity and opportunity. So let's think about, this is an old diagram, but I find it, well, I like this one. This one, this is just showing the electric field component. And it's showing the interaction of this electric field, and imagine there's also magnetic field at 90 degrees, interacting with a particle that's small relative to the wavelength of light, or a particle that is large relative to the wavelength of light. And so thinking about what happens, what the scattering process that occur when you're sort of at either of those ends. So we're going to consider the difference between them. Okay, so when you have the diameter of the particle being much smaller than the wavelength of light, so here's your particle here, right? And here's your wavelength here. So the particle is much smaller than the wavelength of light. It turns out that as the energy passes by this particle, some particles can begin to oscillate, become like an oscillating dipole, right? Because those are particles that will scatter light. That's what happens. So if they begin to oscillate, what happens? An oscillating dipole. It emits. What were you going to say? It emits energy, right? So if it's emitting energy from that oscillating dipole, and there's no loss of energy in the process between the energy that set up the dipole and the dipole oscillation, that's elastic scattering. There's no energy loss. And so when this oscillation induces this radiation of electromagnetic energy, you can imagine that it will be emitted from that particle, which is tiny, in almost uniformly as a function of angle. Almost uniformly. You can see it's a little bit less. This is the direction of propagation. It's a little bit less at 90 degrees. But it's relatively symmetric in the forward and backward directions. Okay. And this is another way of looking at it. So this is the direction of incident light. Wait, is that right? Yeah, 180 degrees. Yeah, this must be incident light because this is backwards. You can look at the amount of scattering at any angle from 0 to 180 and then back around to 0. And this line here represents the intensity of the scattering. So if the light is coming in this direction, if it scatters in the forward direction, it scatters with this intensity. If it scatters in the backward direction, it scatters with this intensity. You can think of these as vectors. This would be the side scatter here and here. This line happens to be for red wavelengths. And this one happens to be for green. So that's a polar plot of the volume scattering. This would be the volume scattering as a function of angle. So again, showing forward scattering is high, side scattering is lower, back scattering is symmetric with forward scattering. So it's two different ways of looking at it. So I just color-coded this as red, and this is green. And you might imagine that blue is even larger. So already you're starting to get a sense of the spectral dependence of the scattering by very small particles. It's going to be highest in the blue and lowest in the red. Blue photons have higher energy, right? So I sort of just sketched one in, right? So you could begin to think about the angular distribution of the scattering as well as the spectral distribution of the scattering. All right. So now when you have the interaction of electromagnetic radiation with particles that are large relative to the wavelength of light, you can imagine that within this particle you have multiple oscillating dipoles, right? And multiple interactions and multiple emissions. And we'll talk about how when the electromagnetic radiation actually penetrates the particle, it sets up these dipoles. We also know that it might reflect off the interface, and we also know that it may diffract around the particle. So there's multiple processes that we see. So here's a diagram from Jerzy Dera's marine physics book, and you can see that we have some rays of light that diffract around the particle, some that enter the particle and bend or refract and then exit the particle. Here's another one that, I'm not sure where this one is originating. This one is kind of coming in and diffracting the other direction. And then we also have reflection off the particle here. Okay. So that's a sort of ray tracing approach. So again, refraction bends in the particle, reflection off the interface in the backward direction, and diffraction bends around the particle. So if we look at the ray diagram for larger particles, we notice that we have a lot more scattering in the forward direction than in the backward direction for larger particles. So I think we'll talk about Fresnel's law when we talk about interface effects in remote sensing. Is that right, Kurt?
There's not much going to be said just because we're not really doing much with surfaces in here.
Okay.
So go ahead and say.
Okay, well, I'll say a little bit about it. So this is where you quantify the reflection and transmission that result from an incident beam as it interacts with an interface. So if you have incident beam of light, some part of it is going to be transmitted across that interface, and some part of it is going to be reflected. And from what we know is that the amount of energy coming in here is equal to the sum of the transmitted and the reflected energy, right? And so it allows you to begin to parse out the fraction of reflection and the fraction of transmission. And it depends upon the incident angle and the difference in the index of refraction from one medium to another. So you might imagine that this might be the water and this might be a particle, and you could look at the transmission and the reflection. And so this part here would look like backscattering. And this, if it exited the particle, would look like forward scattering, but at a different angle. Okay. So, yeah.
I'm sorry, can I take you back to the interaction with small and large particles?
Yes.
I'm not sure I understand the difference. Why is it so different in the scattering of like a large particle and a small particle?
Well, so if you imagine that you have, consider the extreme a single dipole oscillating, right? And so you're looking at the emission in all directions, or the scattering in all directions. But now you imagine you have a big particle. And if you have multiple dipoles in there that are each doing that, and you think of this as waves, right? If you have dipoles within a particle and both of the waves from two different dipoles within the particle come out and they are in phase. You can get constructive interference, and you can get bright spots at that angle, right? You could also imagine that you might have destructive interference somewhere else where the dipoles are coming out like this, and maybe at that angle you'd have destructive interference. And so you have these sort of light and dark, and so often what you see, I can draw it, I have a diagram of it later, but coming out of these particles is not so much, you know, this smooth curve like this. Ooh, that's very bad, I apologize. But often what you really see might be, you know, these lobes here where you have less scattering at that angle and more scattering at that angle and less scattering at that angle because of the constructive and destructive interference. So you've got multiple effects happening within that larger particle in the extreme back down to, say, a single dipole where it's emitting equally in all directions.
Okay, so you have more interaction between the waves
For the big particle, yes, because you've got all these little dipoles in here oscillating. Do you want to add anything, Ken?
A lot of those things are like also cause, you mostly see those with spheres.
Yep.
More than anything else.
Yeah.
So a lot of it is cause these weird resonances that occur inside of the sphere and around the surface of the sphere. And it takes almost nothing to get away from the spherical shape to get rid of a lot of those resonances.
So if you think about the sort of multiple paths of internal reflection that could occur, as well as then, you know, coming out at a different angle. So you're saying as soon as you get to something oblate or, yeah, you don't get the, I don't like to think of it as harmonic, but it's sort of, I think of it more as the constructive and destructive, what's happening in there. And so if you change it so that it isn't all coming in this direction and not coming in this direction.
And the other thing is what Collin drew is for one particular
One particle.
size. So
Yep.
you have maybe a lot of scattering at 23 degrees and almost nothing at 30 degrees and so on. But then you change the size of the particle. Now it's not a lot of scattering at 23,
Right.
maybe a minimum for that particle, and 30 maybe a maximum. So those all blur out.
Yeah, if you have a slightly bigger.
Out in the meat theory lecture next week, where you change do a calculation for one size of particles, look at this plot, do it for another size, look at the plot, but then you add those two plots together, which is what you're doing in the ocean if you have particles of different size, and then they all the little peaks and bumps kind of add out, and you get kind of a smooth curve that's then what you normally say, this is the phase function for typical ocean particles, for example, that have a wide range of sizes.
Yeah, so say the slightly bigger particle had its phase function looking like the purple line. So then you would, if you had this particle with this particle, then you would fill this gap in here, right? Okay. All right, so I use this diagram every time I talk about refraction because it just seems so illustrative to me. And now that I have my kids are playing in band, it makes a lot even more sense. This describes refraction. And so what you've got is you've got band members who are all lined up, playing their instruments, marching in a line down a road, right? And they, strangely enough, get to the end of a road, and there's sand. And so they start walking slower as soon as they get to the sand. So once they hit this sand, they slow down, but the group behind them is still walking quickly. And so by the time that group gets to the sand, it's a lot closer, right? But then these guys march along. They stay separated. It stays constant. If they got back onto the road, the first group would speed up and would separate from the group behind it. But then the second group would reach the concrete, and they would also speed up. And you would end up with the marchers looking just like this on this other part of the road. So the wave, this looks like a wave crest. The wave enters a region for which the speed of the wave slows down, index of refraction, higher index of refraction, and then might exit it and speed back up. Okay, so you can think of this as water, particle, and then on the other side coming out of the particle into the water. So a wave would literally slow down and speed up. By slowing down, it also shortens up. The wavelength will shorten up as it enters the particle. And then when it comes back out of the particle, it lengthens back out again. Okay. So if they were bad marchers, the wave would be coming, or the crest would be coming at an angle to the interface between the water and the particle. Low index of refraction, high index of refraction. So here they're all marching the same speed, but as soon as this person on the end hits the high index of refraction medium, slows down. So slows down as it's propagating. So this person gets behind this person because they're marching slower. Once this person gets onto the sand, they slow down. Right? And so you can see how the marchers bend, or the wave crest bends. And the direction of propagation, because the wave is not entering perpendicular to the interface but at an angle, causes a bending. In addition to the slowing down and shortening up, it also bends the wave. Okay? So that's what happens when light enters the particle and exits the particle. It depends on the angle of the light and the angle of the interface between the two media. And so it will have some impacts on what the light coming out looks like. So it changes its celerity, or the speed of the wave. The relationship is that the wavelength in the medium is proportional to the wavelength outside the medium, and the index of refraction is the ratio of the speed of the wave, the celerity of the wave in the medium or the particle relative to the speed outside the particle. So this would be speed in the particle, speed in the water. Okay. So if it turns out that the index of refraction causes it to slow down, the wavelength will shorten up. If you move into an index of refraction that causes the wave to speed up, it will lengthen. But this is what causes the bending. It's important to recognize that once it exits the particle, it goes back to its original speed or celerity and wavelength. Okay, yeah?
I have a way to remember those things that do not require me to read. What's considered when a photon propagates? Yeah, but in general, what's the conservation principle? Conservation of energy. What's an energy of a photon? Those of you who have H nu, what is nu? So H is time constant, nu is frequency. So frequency is conserved along the path. Now, what's the relationship between frequency, speed, and wavelength? By units, use units.
What did you say, between what?
Between frequency, speed, and wavelength. For any wave.
What's this unit on frequency? So we'll do seconds. Uh-huh.
So 1 over wavelength. C over wavelength. So now you can tell if C since nu is constant and it's equal to C over wavelength. This is constant. If you change the speed, you have to change the wavelength. But if you think in units, often you can.
So sometimes people talk about the period of the wave, like as a water wave comes to shore, the same thing happens. It slows down, it shortens up, but what doesn't change is the period. So if you measure the period of waves coming to shore, you know exactly that it's the same period of the waves that they were when they're out in the open ocean. So, because the period is 1 over the frequency. Okay.
What is celerity?
Celerity is the speed of the wave, the energy. It's the speed at which the energy of the wave propagates. It's separate from velocity, which would describe the speed of matter that moves. You're not moving matter, you're moving energy. So they use the term celerity. So here's my very bad diagram in the animation tools or drawing tools of PowerPoint. So you can imagine that you have a wave, and these are not to scale, but just the wavelengths are big so you can see them. So you have a wave entering a particle. It's entering at an angle, causes it to bend. It slows down and shortens up, and then exits the particle and changes angle back to again, recovering its original wavelength. Okay, but it's coming in at a slightly different angle. You can also imagine that if it came in perpendicular, it would slow down and shorten up and then recover its original speed or celerity, and it would lengthen out again. But if you imagine that there was these are homogeneous, or the propagation of light is coming sort of beyond the particle, and you would have this waves coming in like this. This one does a lot of things, and then when it comes out, they might be out of phase, right? So that's where you can get these light and dark, constructive and destructive interference when you measure out here. Okay. So we talked a little bit about optical cross-section for absorption when we talked about the phytoplankton and where they were absorbing parts of it and how much of its geometric cross-section was actually an optical cross-section where there was absorption and how much was a hole where light could pass right through the cell. You remember that? Nope. Well, we'll just remind you of this. So if you had a cell, and it has a geometric cross-section, and it has some chloroplasts, so that we have the geometric cross-section, which would be the cross-section of the sphere. The optical cross-section would be the cross-section through which there would be absorption. So in this case, the optical cross-section is less than the geometric cross-section. I'd say it's like, 25%, 0.25 maybe. Okay. If we had those really packaged particles filled with chloroplasts, this is going to be less than 1. Here it's probably equal to 1, right? Okay. Well, we have the same thing, the optical cross-section for scattering, right? So you have some light that's going to come through and act like it's not scattered. You can have some light that's reflected. And so you can come up with an optical cross-section to geometric cross-section for scattering as well, right? And if the particle doesn't scatter light, it's 0. And if the particle scatters all the light impingent on that cross-section, it's 1, or somewhere in between. Okay. What happens if I have this scenario? So this is for absorption. What happens to the optical cross-section for scattering here? Huh? 0, because everything got absorbed, right? You're not measuring any light coming out the other side. So it would be 0 for scattering. Wait.
That's not right.
Hmm?
That's not right.
But
Yeah.
Refraction.
we're not there yet. Hold on. I'm not. No, I'm not.
Don't call it
I'll get there. I'm going to talk about diffraction. I'm just talking about just this part, refraction, for right now. Okay.
It's not in the scattering cross-section.
Right. I'm going to get there. I'll correct it when I get there. But I'm just talking about light that's impinging on this part, just on this. Okay? So if this is a totally absorbing particle, it means that none of the light exits and is scattered. Okay? So the problem is, and this is what Ken is alluding to, is that we have diffraction, which causes a bending of the light for light that never touches the particle. Just like waves will refract around a jetty without ever touching the jetty, light will refract around a particle. Okay? And that's what accounts for this really, really strong forward scattering. Okay? So if we, and this is the volume scattering function associated with that. This would be the contribution to the volume scattering function by transmission and reflection. This different amount here is due to diffraction, is due to this process. So this is not accurate because the scattering cross-section is not simply the cross-section, the cross-sectional area of the particle. And it turns out that you can diffract light up to another radius away. So the cross-section is twice the geometric. So if it's a non-absorbing particle, you can have an optical cross-section that is twice your geometric. And there's some particles that would be greater than that, right?
I mean, actually, if you
It's the
add
cross-section.
R, it's going to be 4 times.
4 times. It's 2 times D.
So this is 4.
Yeah, 4R or 2D. No, it's not. No, it's not 2D. Yeah. So the area is twice.
Yes, but it's not twice the radius.
It's not twice the radius.
Yeah.
Right.
And that's for a very large particle.
Yes, for very large particles,
But in between, it can be even bigger.
the optical over the geometric cross-section can be 2, and for some particles can be larger. So if there's no absorption in here, then that means that's all attributed to scattering. If it's an absorbing particle, this contribution is due to absorption, and the part away from the cell is due to diffraction. Okay. So absorption impacts the scattering. And so you'll see a lot of papers that talk about modeling of non-absorbing spheres. And so they're ignoring the fact that something is happening in this cell or in this particle in terms of absorption that's reducing the scattered light that you would measure if you had no absorption in that particle. Okay.
I'm very confused. What's the definition of scattering? Is it change in angle or change in the frequency of the wave? So
Yes.
I'm thinking, what happens if light travels from an atmosphere with a certain composition of gases to another atmosphere with a different composition of gases? Would that change?
Well, the gases will absorb differently. So that's number one,
Yeah.
right?
And how would it scatter with that?
It might scatter differently if the particles have different sizes or different concentrations. I mean, so think about a particle of light being scattered by a particle, right? So what if the light went through, slowed down, sped up, and you detected it with your detector? If it came at exactly the same angle and exactly the same phase, you would call it unscattered. Ken, would you technically call it scattered if it went through the particle and slowed down?
And slow down, yeah, it is.
It's technically scattering, but you would never measure it, right? Because it's been impacted by,
Instrument
Oh, right.
Measured
Right.
0 degree scattering.
0 degree scattering. Because that's the big question. So if you have light that comes out here at 0 degrees, it's gone through the particle, its phases change, but you wouldn't detect it. Now, for our purposes, is it meaningful? No, because we're interested in how light propagates through the ocean, and it's going to propagate through the ocean as if it were not scattered. But technically,
So kind of the definition of forward scattering is always scattering the forward direction except in the 0 degree. That's that definition.
but if it changes phase, it's
You have
still
to-
scattered.
Not to, there's a definition issue. So forward scattering is any scattering in the forward hemisphere. What Collin is not talking to is when it goes in the same direction as the light came from. So really the
This.
zero angle of the VSF, which is not the same as the forward scattering.
Right.
As the integral of the VSF.
Right.
In the forward hemisphere.
So this is forward scattering. That's forward scattering, right? And if you integrate all of this, that's the forward scattering coefficient. But the scattering at 0 degrees. So,
What did we say about the phase? If that changes, will that
so it will change the speed as it goes through the particle, and it will go back to its original speed when it comes out, but it can be at a different phase.
If we have a
Instead of doing this, this one goes through the particle. When they come out the other side, they're not coming out together. They could be coming out this way, out of phase. And then you would recognize it as scattered light. And the instrument, that's what the instrument that Ed Fry did, measured that phase change of the forward scattered light. Right.
I mean, it's totally irrelevant almost.
It is. But it's interesting. It's just trying to get a sense of what's happening to the light as it goes through these particles and around these particles. And when we're measuring it, what is it that we're measuring? And when we have a sensor that measures, has some solid angle of measuring, and it's saying that every photon that I measure in this detector is unscattered, that's not true. So, okay, I'm going to make a smaller one. That's not true. I'm going to make a smaller one. Well, I don't have any signal left, so I can't measure it anyway. So there you are. Yeah. Okay. So it turns out that the diffraction pattern that you might measure on the other side, this is image of, if you have particles, this is a distribution of spheres, suspended spheres. These are little rectangles. You shine light and you measure the diffraction pattern on the other side of this. You can see that the diffraction pattern, this is symmetric. This one is, well, it's symmetric, but it's not symmetric about the azimuth. And so that's the effect of shape on the diffraction pattern. Right? And the diffraction is most of the scattering, so it's important. That's the basis for the design of the list. And we'll talk about the list on Friday. We'll work with the list on Friday. Yes? Yes, okay. So the list measures the diffraction, it measures the forward scattering in the first approximately 20 degrees and resolves the intensity of scattering at each one of those angles. And from that, because it's the light that is predominantly the light that's traveling around the particles, it's very sensitive to particle size. And so by measuring the forward volume scattering function, you can invert it for the size of the particles. So what influences the refractive index, or how much the light slows down within the particles? This is from a nice experiment that Stramsky did, where he looked at the index of refraction as a function of the concentration of carbon by those particles, but these were phytoplankton, and found that the more enriched the particles were, the carbon of the particles, the higher the index of refraction. And so carbon-rich particles scattered light more effectively. This is another study by Mike Twodarski in 2001 and his colleagues. I think Manuel was on that paper as well, which looks at how the fraction of total scattering that's in the backward direction, that's what this is. So this is 3% of the light scattering in the backward direction, 1% of the light is scattered in the backward direction compared to total. This is a description of the size of the particles, and each one of these lines is an index of refraction. And so particles that would be in this part of the graph would be highly refractive particles like mineral particles. Particles that will be down in this part of the graph are weakly refractive particles. So when he took out and made these measurements in the ocean, what he found is that he found a group of particles that mapped out here. It turns out that was in a chlorophyll maximum. He found a group of particles that mapped out in this region here. They tended to be more detrital organic particles. And then he had a resuspension layer, I believe, where it was more mineralic, inorganic particles that mapped out here, which suggests that mineral particles are highly refractive and phytoplankton particles are not highly refractive. So phytoplankton are pretty weak backscatterers, maybe 0.5%. Organic detrital particles are maybe 1% backscattering. And mineralic particles are much, much higher in backscattering. So when you work with Kurt and hydrolite, and one of the inputs you get to say is, what is the backscattering fraction? What's the backscattering ratio? Well, it depends on who's in the water or what's in the water. So you can think about that. Right? It depends on the composition of the material. Let's see.
One thing to say.
Yep.
This diagram is based on meat theory.
Me theory, yeah.
So it's assumed homogeneous spheres.
Yes, but the data are not.
The data are not.
Yeah.
It's kind of amazing that this is not a problem.
Yes. So the effective absorption, I think we talked about here. We parameterize absorption by the imaginary index of refraction. And so you have to remember that that part of the light is being attenuated by absorption as it goes through there, and it affects the scattering. We don't need to do this. This is something from yesterday. Forget this. Okay. So what that means is that if you have really, really strong absorption, you don't have scattered light emanating from the particle if you're absorbing all the light that's impinging on the particle. And you'll only see diffraction. Okay. So the things that we need to think about are particle size, particle composition, particle shape, and the internal structures of the particles that will help us understand the scattering properties of those particles. So who's scattering? Well, water molecules are scattering. We have a question about dissolved matter, right? Did you guys figure that out yesterday? Did we have scattering by CDUM? Huh?
Not a lot.
Not a lot. In fact, you had more absorption than you scattering. So not a lot. But it's worth to continue looking at it. It's still an active area of research. And then we have particulate and we have organic and inorganic particles. All right. I think in interest of time, we'll talk about size. We're talking about size on Friday, but just size matters with regards to scattering. And the size of particles in the ocean varies significantly, and we'll be able to figure out how to characterize the size of particles in the ocean. This is a diagram that Kurt's going to show you, which is, again, the volume scattering function or the phase function for small particle scattering that's color-coded. So forward scattering, side scattering, color-coded, just so you've seen it and you'll see it again in a little bit. We talked about how the volume scattering function was really different for different wavelengths. And so for very small particles, we tend to see very strong scattering in the blue and very low scattering in the red. Okay. So this becomes important when we were thinking about how you correct if you appear to have scattering in your AC meters with that little offset. if you have this offset and you think that it's scattering, if you just subtract this, are you subtracting for the scattering by the small particles in your CDOM? No, not if the scattering by small particles looks like this, right? So really, here, 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 which one is it? So thinking about what this means becomes very important if you think about how you might correct it, considering that small particles scatter blue light more. Okay.
Yeah.
Yeah.
This is a simple question, but aerosol size, how does
Mhm.
it compare to these particle sizes in the ocean, like water vapor or?
So aerosols in the atmosphere are large, considered large particles. They have relatively flat scattering. At least that's the assumption that we make. Yeah. The gases don't. So the scattering by water in the ocean is going to be a function of temperature and the kinetic energy because of the clusters of how the water molecules cluster together and act like particles and density, gradients in density. That's what will be scattering in the ocean. And we know that the clusters are a function of temperature, so that scattering should be a function of temperature. The same thing with salts, and here's a nice study that came out in 2009 where they actually looked at the increase in scattering as you increase the concentration of salt in your seawater. So you get about a 30% increase in scattering, and they measured the volume scattering function of salt water, and it compared very well to Morell's measurements from the 70s. Scattering by viruses. This is a paper by Barney Balch where he looked at a couple of different viruses, and they have sizes on the order of 100 nanometers, right? And they look like this scary alien. And he actually measured the volume scattering function of the viruses and found that they were much higher than the water volume scattering function. I'm not sure if that's ever been validated in the ocean. And most of the viruses are actually in particles. So most viruses would be in particles. So free-floating viruses is really low concentration.
Concentration of viruses converted these concentrations into measured their distribution as they were.
Yeah. Yeah, they don't really matter unless they're in you. Colloids. There's a big interest in looking at colloids and the effect of scattering on colloids. So there's a couple of papers to look at that we'll put on the drive. And you can see the size of these particles and then look at the scattering spectra of pure seawater versus seawater with colloids. So that would be this question here. Is that the scattering by the colloids? This is a slide that I took from a manual where he says there's no evidence in the literature that scattering is significant, but the place that you observed it was in pore waters of sediments. That's Emmanuel diving with an AC-9 on his back and a tube, pumping up pore waters through the tube.
You were 0.2 micron picture.
Yeah.
That's the only time I've seen a significant difference in
Have you repeated the experiment?
I mean, I wish.
Yes.
I wish anything.
So this is phytoplankton. There's some work from Dariusz Stramski looking at the phase function or the normalized volume scattering function as a function of angle for various phytoplankton. And the scattering spectra for various phytoplankton. And you can see here there's very strong dips in the scattering spectrum right around 676. Why do you think that is? Yeah, chlorophyll absorption. So it's this effect here, right? If the light gets absorbed, it can't be scattered. Here's some Saharan dust. They did some experiments. This is some other work from Dariusz where they looked at the size distribution of dust, and then they did some mass-specific scattering measurements. I think some of these were measurements and some of these were models to show the spectrum of scattering of dust, which is very small and has some spectral dependence to the scattering. The larger particles tend to scatter equally at all wavelengths. So large particles don't have a spectral dependence. Bubbles. This is the fraction of bubbles as a function of wind speed. Here's the size of bubbles, the size distribution of bubbles. It turns out there's some minimum. They present here that bubbles can't be any smaller than 15 microns. Is that right, Ken? 15 microns. They couldn't, or they either couldn't measure, or they said there appear to be no bubbles that are less than 15 microns. Yeah, I know. But and then looking at the scattering and the backscattering as a function of the bubble concentration. So you can see that when the bubble concentration is really high, it's above the background scattering for pure seawater. So bubbles are bad in your spectrophotometer, but they also scatter light in the actual ocean. And this is a volume scattering function modeled for bubbles. And again, you can see this. These oscillation features caused by the sphere and that interaction that Ken was talking about. So me theory describes the interaction between electromagnetic radiation and particles, and it makes a lot of assumptions, and Emmanuel's going to talk about me theory. And it's a very useful tool for validating measurements that you might be making. And so I think you'll have a lab where you'll actually get to look at the prediction of particle scattering off of individual particles and also off of a complete suite of particles. These would be an example for 5-micron particles. This is if you look at particles with the same index of refraction but different sizes, and you can see the volume scattering function is really, really different depending upon the size of the particle because of those sort of internal reflections and constructive and destructive interference of the waves going through. So I think we're going to talk a little bit more about this later, so I might quit here and go to this.
Collin, we can do Kurt tomorrow. We have the room so we can do just your talk today. We're doing the absorption lab this afternoon, particularly. So we can do the full
Okay.
talk and then Kurt will be.
Well, I can just show a couple of things, but I think we should stand up and take a breath, because if you're as hot as I am up here.
You want to take a 5-minute break?
Yeah, and then we'll just talk about the volume scattering function as a function of a couple of different properties.
Yeah, I'm cool with that. Whatever you want to do. What would that come down the road tomorrow?
Well, I
When a beam impinges the ocean, its wavelength change. Is that what I understood? Okay, so like blue photon above water is no longer, well, a little less blue.
It's a little more UV.
Right.
So, but then what happens is it goes to your sensor,
Right.
which goes through Teflon, which then goes back through air,
What is it?
which then goes back to the detector.
This is
So
when you
So you
accept
get to
your-
the other side. I know, because you think about like, how come I don't see the light differently when I go underwater? And it's because you put a mask on and it goes back. So basically the light is coming through air and then goes through your eye, right? In the mask, when you go underwater, it changes in the water, it comes back through the plastic, it changes, it goes back to the air, goes back to what you had up here, and then goes into your eye. So what you see in the air and what you see underwater in your mask is the same, but it has changed as it's gone through.
That's new for me. I never thought it that way.
Yeah. And so the energy is conserved. So the energy of the photon